Hi. Today we'll continue what we started on chapter 2. And remember we talked about projectile motion in the previous lecture. And we covered all the types of firing an object under gravity. We had the symmetric and 3 non-symmetric firing. What we developed so far in a projectile motion, we said we have horizontal motion in X and vertical motion in Y. So when you do any calculation horizontally in any type of projectile, you have one equation only to use. You don't have to list the 5 items. You just have one equation. It says displacement horizontally equal initial velocity multiplied by cosine theta naught, firing angle, multiplied by the time between the 2 points, start and finish. So horizontally you have one equation. What else we have? We have one statement horizontally, which says because there is no acceleration in X, final velocity in X at any point is equal initial velocity. And remember, initial velocity means V naught cosine theta naught. So you need this and this, because this is a repeat of what I'm saying. And this is a statement. AX always 0. So this is anything to do with horizontal motion. A projectile, you have one equation and one statement. It's an equation, but it says Vx doesn't change. Everywhere is the same. Vertically, you have 3 equations of motion, which are equations of free fall, because it's under gravity. The first one, final velocity in Y equal initial velocity in Y, which is V naught sine theta naught, minus gt. Second, final velocity in Y square, initial velocity Y in square, minus 2g displacement vertical, and displacement vertical initial velocity in Y multiplied by the time minus half gt square. So any question of projectile, just remember this table. 3 equations in Y, 1 equation in X, and 1 statement. Now, a special case, when you have a symmetric projectile, what you add to these 2 equations? H max is V naught square sine square theta naught over 2g. And the second one, about the range, maximum delta x. It's V naught square sine twice of the firing angle over g. Again, those 2 for symmetric only. No, it will be given, but not in details like these are major. Remember, these 3 are mentioned in chapter 2. The only difference is that sine theta. So they are free fall, but the angle sine theta. So this is the summary of projectile motion. Okay. Now, what I'll do today, I'll discuss a little bit more about the range R in symmetric. And then I move to an applications of motion in 2 dimensions in circular motion. Okay, once we finish that, then we'll start doing some problem solving. So range, R. R, it's V naught square sine theta 2 theta naught over G. And remember, this is for symmetric only. So let's take a symmetric case. You fire from a level and back to the same level. Start and finish. Now, where is the range? The range is delta x max. R is delta X max. Now, I want you to look at the equation here, R, range, and tell me the range which you want to calculate depends on what factors in the equation here? Depends on initial V naught and the angle. Right. This is the initial velocity of throwing or firing. If you increase it, but you fix the angle, don't change the angle of firing. Keep it like at 30 or at 40, whatever. And you increase V naught, what happens to the range? Increases. So if you want to maximize the range, change the velocity. Yes, maximize it as much as you can. But remember, velocity cannot be just increased forever because you have a limit for the velocity. It depends on the machine, the system maybe, which fires. Or if it's a human body, so this depends on how strong you are and what is the fastest speed you can reach with throwing something, yeah? So this is one factor, the speed of throwing. Now let's say this time you fix the speed of, let's say you always throw with 10 meters per second. Okay? Now if I want to maximize R, increase R, what should I do? I have to change the angle. But here the R depends on the angle or depends on sine of the angle, which means you have to maximize sine. What's the maximum value of a sine? So R can reach maximum value if sine twice of theta naught equal 1, what happens? R will be R max. Okay? Now when this is equal to 1, how much is 2 theta naught? 90 degrees. So what is theta naught? So what is the best angle to have a maximum or maximized range? Now this is something you have to know. Whenever you want to maximize, if you want to throw something and it's not reaching the target, what you should do? Angle it at 45 to increase the range. Of course, the faster, the farther it gets. You can increase R in two things, V naught and theta naught. Yes? Now this technique can be used when you want to win, like Ghazal, she's an athlete. I went good. If you want to have a long jump, you run, you come at high speed. Why you come at high speed? Because you want to jump, yes? When you jump, what's the type of jump you have? Symmetric or non-symmetric? So you are like a projectile. Now when you come running, what do you usually try to do?
Jump at 45 degrees.
First, you want to reach the line with the highest speed, yes? Which is V naught. And then from here, you have to jump at what angle?
45.
This way, you guaranteed you get the R max, yeah? So you have to train yourself to come at very high speed to the point. And then when you come to the point, don't stop because you reduce V naught. So you have to have the technique that you coordinate your foot with your body. Eh? So the moment you step on the line, you already have the maximum velocity. It's not like you slow down. And then you have to train yourself to jump at 45. You do that, you can get maximum R. So what is R max? When this is equal to 1, then it depends on V naught and G is constant. So sometimes we write R max as V naught square over G. This is R max because this one, of course, this is 1 because the angle is 45. But still, you can keep this and put 45 for, which is 1 here, 90. So this is about range, yeah? A part which we didn't cover. What else about symmetric? I'm talking about symmetric here. Not about maximum range, just range in general. If you have, let's say, there is a target here, and you are here and you want to hit this target. And let's say you fire it with V naught, and the angle here, let's say, is 10 degrees. The speed could be 20, whatever. When you have this V naught and this 10 degree, you see that this goes and hits the target exactly at this R. This is not R max, because this is 45, not 45. Now, if you keep the speed the same, V naught, but you increase it to 45, what happens?
The R changes.
So will you hit the target or beyond the target? So if it's 45, if this is 45, it goes and hits beyond. This is R max. Now, what happens if I fire above 45? It will come back or not? Okay. So is there a possibility that there is another angle when I fire it hits the same target with 10 degrees?
Yes.
So there is an angle above 45. It gives you the same range. Okay? So usually there are two angles which you can use to hit a target. One below 45, one. Okay, the other one which is above 45, how much is it?
90.
Remember symmetry, yeah. 80. This is the center, 45. Now, the first one was at what? 10. So 10, how far 10 is from 45? 35. So it means if this is the center, you need one above 45 by how much? 35, above it. So if you add 35 here, what's the total? 8. You add them. Or just use this rule. 90 minus the first angle, it gives you the second angle. 90 minus 10. So you can hit the same target with 80 degrees as well. Either 10 or 8. You got it? So a target can be hit with two angles in symmetric firing. One below 45, one above 45. Both will hit the same target. But if you fire with 45, you have one angle only, 45. And this is the maximum range. Either you hit the target at maximum or you don't. Now, this is the question which I ask usually. What's the difference between firing at 10 or at 80? Because at 10 or 80, you hit the same target. You accomplish what you want. You achieve the goal, yeah? You hit the target. Which one you prefer to use? Low angle or high angle? And why? High. Who said high? High. Why high? She said high angle. Why you prefer the high angle to hit the target?
Because sometimes there are stuff that are beyond, so that you don't hit the thing.
What you mean beyond or between? Between the target and the point of launching, yeah? If there is a mountain here, and you want to hit this target, will you be able to? No. With a small angle? You hit the mountain, yes? So you have to use above. So the advantage of high angles or big angles is to hit a target behind an obstacle. Okay? So if I want to throw this pen to the back and hit one of the students in the back, if I use a small angle and one of you stands up, I hit her before I hit. Okay? So I have to use an angle above 45 to avoid, yeah? Okay, this is an advantage, yeah? But tell me about a disadvantage.
The disadvantage that we will get, it will be slower.
Okay, now the word is slower and faster. Be careful, be careful. Yeah, you're talking about velocity and speed, yes? But I'm sure you don't mean that, slower and fast. What do you mean? Time. Which one takes longer time? The low angle, yeah? So it means this will take shorter time to hit the target, but that one? Okay, so don't use the words fast and so, because fast means fast velocity is high, yeah? The velocity is the same in both cases. You don't change V naught. V naught is the same. But what you're changing? Angle on. So it takes shorter time, yeah? But that one takes longer time maybe. That's a disadvantage, okay? So that's the reason.
Here the velocity is constant.
Yeah, because I'm doing an experiment. When you do an experiment, you don't change all the factors. You fix V naught, but you change the angle only. You can't change both.
What if I fix R and then...
Well, this is what you did. You fix R, you want to hit the same target.
So the velocity of...
And the velocity, you have to fix it as well. So you just change the angle. No, don't talk about R. Talk about V naught and theta naught. You fix one of them.
No, because I started comparing between V and theta.
No, don't compare V naught and theta, no. No, we just want to know what's the effect of these two on R. On R. So you do them one by one, not both. You can do both, but maybe one increases, one, or both increases, or both. We don't want this. When you want to know the relationship between things and you have more than one factor, what you have to do, you have to fix all factors except you change that one to see the effects. And then you fix the rest and you change another one. This way you understand. Like in math, they call it when you have partial derivative. Why you do partial derivative? Because you have x, y, z, yeah? And you want to know the effect on the function. Will you differentiate all? Or you fix two, you differentiate, and then you fix another two, differentiate, and then fix another two. This way you do partial to know the overall relationship. You cannot change them all three at the same time. All right, I hope this is clear now, yeah? About the range. Any question now here about it? Okay, so this is just explanations of the range. Now we move to the last part of this chapter. The last part, it's about uniform circular motion. Uniform circular motion. Remember, we are in a chapter which deals with motion in 2 and 3 dimensions. Now, if you have an object circulate around the center, how many dimensions do we have? X, plane. Something circulates, or something circulates in a plane. X and? So this is an example of motion in 2 dimensions. So let's cover this. So we have an object circulate, moves in 2 dimensions, in circular motion. Now, what's so special about this circular motion? It is uniform. The word uniform in general means constant. Constant, yeah? So here, what is constant?
The motion.
Yeah, but uniform here it's what usually we say uniform motion. Either you're talking about the velocity or the acceleration. If you say uniform velocity, means constant. Uniform acceleration, constant. So you have to know now here, the uniform, what does it mean? I'll explain it only. I'm just saying uniform means constant, something constant, something constant. This is the x-axis, this is the y-axis. And let's say this is the center, 0, 0, and there's something circulate around there. And this is the object here to start with at point 1. And the possibilities for rotation or for circulation is either clockwise or anti-clockwise. It doesn't matter. So I'll take the anti-clockwise. So let's say it rotates this way, anti-clockwise. So to start with, it's here. Then it goes to point 2, then point 3, 4, 5, 6, 7, 8, and back to 1. Right. This is real motion. This is not a function, xy function. No, this is something moving on this path. When the object at 1, while it's circulating, what is the direction of velocity here? Velocity is a vector. Okay? How do you draw velocity at point 1 when something circulates? We said this before, like tangent, yeah? Like projectile tangent, tangent to the path. So if I want to draw velocity 1 here, I say velocity 1 is tangent v1 as a vector. At 2, tangent. At 3, tangent. 4, tangent. 5, 6, 7. So these are the velocity vectors of something circulating, tangent. Of course, from here to there is the radius, yeah? R. Now, when we say uniform circular motion, we means that this object rotates at a constant speed. So uniform mean here speed equal constant. The speed of circulation is constant. It doesn't change. Okay. Example of something similar to this. You remember the old ceiling, fan ceiling? Okay. When you switch it on in the beginning, the speed is constant or changing? Changing. So start from 0, change until it reaches the steady state. Yeah. When it reaches the steady state, we call it uniform circular constant speed. Pay attention, I'm using the word speed. I didn't say velocity. Speed, the value. The value. Now here, if I follow the velocity now, the speed is constant, like 4 meters per second, 5 meters per, doesn't change the speed. The velocity at point 1, velocity is a vector. Which way is going? This way. Yes? At point 2, what happened? Change the direction or not? Change. And 3? Change. So what happens in circular motion? To the velocity keeps direction. Okay? So the velocity is constant or variable? As a vector. As a vector, it's changing direction all the time. All right? Now, how do you find acceleration or acceleration average, generally speaking? What is acceleration average equal to? delta V over delta T. And delta V means V final minus V initial over delta T. All right? Now, if the object moves on a straight line, like in chapter 2, motion in one dimension, what we had, acceleration average equal final velocity minus initial over time. And what were the possibility at that time? The initial velocity either positive or this one positive or, so that at the end when you subtract delta V either positive, so to the right or to the left. That was when you move in one dimension, yeah? But in chapter 4, motion in space. So when you say V1, what is V1? Not positive or negative, it's a vector. And when you say V final, you mean final velocity vector. And when you say delta V, you mean delta V vector. And when you say average acceleration, you mean acceleration average vector. Vectors, yeah? Right. This tells you that acceleration depends on the velocity vectors. And vectors are, they have directions and magnitude, yeah? Right. Let me give you this example, and then we go back to this one. Suppose I'm going this way. For you, this is the right-hand side, yeah? My velocity is positive or negative? Positive. Okay, I start here with a speed, not velocity, but this way. I will not change my direction. If I start here moving at 4 meters per second and I do this, I'm changing my speed or not? So maybe from 4 to 7, yes? Did I change the speed? Yes. Okay, when you change the speed, do you have acceleration or not? Yes. So you can generate acceleration by changing the speed. But did I change the direction? No. Okay, so this is the first way of generating acceleration. You can write it down. To generate acceleration, we can do it in different ways, yeah? First, to generate acceleration, it can be done in 3 ways, maybe. The first way or first method, by changing the speed only, without changing the direction. Right? Now, second, what do you think? To generate acceleration, what we have to do? Look here on the board. Look on the board. Look at, this is an example. When I have uniform circular motion, the speed changes? Doesn't. So do I have acceleration? You don't know. Yes? Some of you will say yes, some of you say no. She said no, she said yes. Anyway, it doesn't matter. So it's 50-50. Some say yes, some no. Now let's discuss it. To generate acceleration, acceleration depends on what? V final. But V initial means speed or velocity. And it's a vector. So when you subtract those two vectors, what's the final answer? Another vector. So is it possible these two vectors, they have the same magnitude? And this is what happens here, same speed. So here, if you look here, when I say what is V1 magnitude? What is that speed at 1? What's the speed at 2? Equal to V2 magnitude, equal to V3 magnitude, and so on. Speed, constant. So the speed here is equal to speed here, equal to speed here, everywhere. Instantaneous, of course, yeah? But can I say V1 vector equal to V2 vector? No. Why? Because V1 vector is going this way. V2, changing direction, different. What's the proof? If I ask you about this vector, how would you write this vector? What's the angle of this vector? 90. So it's J only, yes? So it's V1 magnitude J, no I. What about 3? Minus I. 2 minus I plus j. 4 minus, okay? So look, those vectors are not equal, but their magnitude is always the same speed. So if these vectors are not equal, when you substitute these two here, not equal, like you take any two, will you get equal to 0 or equal to a value? But remember, I didn't change the speed. I changed the direction only. So at the end, do we have an acceleration or not? How I generated this acceleration? By changing the direction only. And this is important. You can generate acceleration by changing the direction of velocity only. So this is the second way. You can change the velocity direction, but you don't change the magnitude, the speed. This is the second way. Now you tell me the third way to generate acceleration. Both. If you change the magnitude, the speed, and at the same time you change the direction, then you can generate acceleration as well. So you have three ways to generate acceleration. Change the magnitude of speed, change the magnitude only, change the direction only, or change the magnitude and direction. Three ways. Now, I gave you the first two, yes? Example? First, second. I need an example about the third, changing the magnitude and direction. Look here on the board. And remember the example I say when you switch on the fan, when you switch on in the beginning, the speed is constant or variable? So there is a change in speed. What about its velocity? So this is an example of both. At the beginning, when it starts, increases. The speed changes and the vector of velocity always changing. Of course, I'm talking about the tip of the fan, tip. Or any point which has a radius. Just fix the point and follow this point. You see, this point is changing direction. Right. So do we have acceleration when we have uniform circular motion or not? We have. So we have to calculate it. How? What's the magnitude? What's the? This is the formula to find average acceleration. But it doesn't matter. Average, we can change it to instantaneous. How? By taking the limit. Yeah? So let's see if we can have an idea about the acceleration average here. I don't need this. Let's remove this one. Let's say, because I need start and finish point. Let's say this is my starting point, point 1, and I finish at 3. Okay? Start 1, finish at 3. What I want to calculate? Average. Okay. Because I have vectors, remember, whenever you have vectors, you have the freedom of draw them anywhere you like in the page, as long as you keep two things. The same magnitude, same. So instead of doing my drawing here, I'll do the drawing here, between 1 and 3, here. I put a small x and y. Now I draw V1. V1 here is what? Going up, V1. What's the magnitude? Is that much, yeah? V3, same magnitude or not? But direction? Now, can I shift this one here or not? Yes, but just keep the same magnitude, same. So I'll draw it from 0, 0. This is V3. Now I have V1 and V3 starting from the same point. When you want acceleration, what do you need? Delta V vector. Delta V vector means subtractions of vectors. Vector 1, vector 2. Where is the subtraction here? If I want to draw the subtraction. This is, let's say, this is vector A, this is vector B. They start from the same point. Where is the delta? From head to? Not between. Between is plus. So in this drawing, where is the delta? From tip to tip. Pointing to which one? To the final. You're going from 1 to 3. So this is the direction of delta V vector. Right. If you know delta V, and you divide it by the time taken between 1 and 3, what do you find? Acceleration average vector. The direction of delta V and A are different or the same? Same. If you know the direction of delta V, you know the direction of? So where is A here? Same, this way. Yes? Same, parallel to delta, or on delta V, same. Let's take another 2 points. Start at 3, finish at, and I'll draw it here. 3, this is 0, 0, V3, 5. Where is the delta here? From 3 to pointing to 5. This is delta V. So what is the direction of A average? Same or different? Parallel to this one. Let's take another 2. I start at 5, finish at 7. I'll draw them here. 5 initial, down. 7 final. Where is the delta? From 5 to pointing to 7. Where is the acceleration? Same direction. Seven to 1, back to 1. Cross. Initial 7. Final 1. Where is the delta? From 7 to 1. So where is acceleration? Parallel to it. I'm back to the same point, yes? Look at the diagram and tell me what can you conclude about the direction only of the acceleration here?
So it's the same as what the
Of course it's the same. We know this because if you know the direction of this vector, same as the direction of this one. That's why I put them parallel, yeah? No, something else. Acceleration here pointing to the inside of the circle. Yes? Here? So what's the conclusion? The acceleration always pointing towards the inside. You're not sure if it's toward the center or not, but to the inside, not to the outside. So when you have uniform circular motion, do we have acceleration or not? Which way is pointing? Always towards the inside, yes? Now, these are average acceleration. If I want instantaneous, what I have to do to this equation? Take the limit. When delta t approaches 0. Delta v, delta t. Of course, this side, limit, A average. Remember, when you take the limit, it becomes what? An instantaneous acceleration. Huh? We said this many times. Whenever you have an average function and you want the instantaneous, take the limit of both sides. Take the limit, what does it mean here? The delta t approaches? Okay, when I do the drawing again, if I say this is 0.1, where is the final? I can't take 3 as a final, too far, yes? The delta t between those 2 points is high. So what I say, I start here, I finish a point very close to it, yeah? So delta t, small. This is like another one, yeah? When you draw V1 and you draw V2 very, very close to V1, and you draw delta V to connect the heads, because they are equal from the geometry, it's not, I will not cover it here because it needs to drawing and mathematics. But what I want to say that when you draw delta V, you'll find it's pointing exactly towards the center. Not just to the inside, exactly towards the. So at 1, what's the acceleration direction? Towards the center. At 2, towards the center. At 3, towards the center. At any point, you have an acceleration pointing towards the center. This acceleration in circular motion, which points always towards the center, we have a name for it. We call it centripetal acceleration. Centripetal acceleration. The symbol is A sub C, centripetal acceleration. Now, why we call it centripetal acceleration? Because the word center, it means towards the centripetal. So here, when I say where is A, you say A towards the center, and you put A sub C. Here, A sub C. Here, A sub C. Always pointing towards the center. What can you tell me about the direction of AC and V at any point? Perpendicular. Huh? Always 90. Right. The AC, centripetal acceleration, its direction constant or changes? Does it point on the same direction all the time or changes? I want to hear. Changes or it has the same direction all the time? How come same? As a vector. It always points to the, but it points in different ways, yeah? Okay, so this is how you describe centripetal acceleration. You say centripetal acceleration is always pointing towards the center. But as a vector, it doesn't have a specific direction, yeah? Like here. What's the direction of AC here as a vector? Minus I. Here? Minus J. But here? Minus I minus J. But in all these cases, always pointing to the center. Okay? Now, centripetal acceleration, we have another name for it. We call it radial acceleration. So if we ask you what is centripetal or radial, means the same thing. Why we call it radial? Because it's towards the radius. Where is the radius? This is the radius or not? Yeah. Radius, R, yeah? Radial. Same. Now I know the direction. Always towards the. What is the magnitude of this? We have to calculate its magnitude, yeah? Again, here you need some geometry and mathematics, which is in the textbook. I don't want to put it here on the board, because at the end of the day, I need the equation. If you are interested, just go and check this in the textbook, how we found this formula. Now, after doing all the geometry and applying the equation of acceleration, you'll come up with this equation, saying that centripetal acceleration magnitude is always equal to v squared over the radius. What is v here? V usually is velocity, yes? But when you square velocity, it means v dot v. So it becomes a speed, scalar. So, okay, we write v, but we mean speed, s, yes? So this is speed square over radius. Or the magnitude of the velocity, okay, over radius, yeah? And what's the unit? Meter per second square. Okay. Now, let me draw a circle here. And let's say this is you here at this point, and this is the center. One of you. If you walk, start from here. You walk around the circle and back to the same point, and this is the radius, of course, yes? You start here, like me. I start here, I go around, and back to the same point, yes? Is this a distance or displacement? Distance. How much is this distance in a circle? How do you calculate it? What's the name of it? Circumference. So this distance, start here, back to there, is the circumference, yeah? The symbol for circumference is C. What's the formula? 2 pi multiplied by the radius. What's the unit? Depends on R. If R in meter is meter, centimeter, centimeter, millimeter, millimeter, yes? Okay, so C is a distance. Okay, now again, start from here, go around and back to there. How much time did you spend from here back to there? When I say how much time, I don't want you to give me a specific time. What do you call this time if you start from here back to there? Yes? Period. Good, very good. Time of one revolution. So from here back to there, we call it capital T. Capital T is time for one revolution. Or one what? Cycle. Cycle. The word revolution, we abbreviate it to rev. R-E-V, rev, yeah? Rev. Okay. Now, C is the distance from here back to there. What is the time from here back to there? Capital. If I divide the distance over the time, what we get? Why are you shy to talk? Either you say it louder or keep silent. I cannot hear. If you divide the C over the T. Look, someone said velocity, someone said speed. Average speed. Which one I believe? Distance over time. Average speed. Not speed. But does it matter here to say average speed or speed? Because the speed is? So average, instantaneous, both are the same. And what I call speed here, I call it V as well, yeah? So what we say, V is C over capital T. And what is C? 2 pi R over capital T. So at the end, we'll have V equal 2 pi R over the period. This is the equation which you need. And the unit, if it's meter per second, of course, if it's R in meter. So how many equations we have now? 2. Acceleration centripetal V square over R, and V is 2 pi R over T. Good. What is left? We have one conversion factor. Conversion factor. When objects rotate, circulate, sometimes we don't talk by using meter per second about how fast something going. Especially mechanical engineering. When something rotates, a motor, they say, what's the rate of rotation? It says RPM. RPM, which means revolution per minute. So what they use is revolutions, not meter per second, kilometer per hour, or mile per hour, yes? Revolution per, Okay, now if you want to use these equations, V measured in what? So you can't. You have to change this rate to a speed units to use it, yes? So we have a conversion factor. How to change it from revolutions to meters or from meters to revolutions, okay? Now, start here. You go and back to there. How many revolutions? Revolution. How many meters or kilometers did you walk? 2 pi r. So this is the conversion. You say 1 revolution is equivalent to 2 pi r. Now what's the unit? I don't know. Maybe meter, kilometer. It depends on r unit. Okay? So this is your conversion factor. Now let me give you an example on this one. Example. An object rotates at a rate of 40 rev per minute. Revolution per minute. At a radius of 2 meters. An object rotates at this rate, 40 rev per minute. And the radius is 2 meters of this object. Calculate the centripetal acceleration of the object. What's the centripetal acceleration? Right? Now, look here. You have 2 formulas. 1, 2, and 1 conversion. What's the question? Find AC. To find AC, what you need? Radius, speed. Radius is given? The speed is given? Remember, speed is in meter per second. This is revolutions. So what you have to do? You have to convert this one to a V unit, yeah? Then you can use it. So how you do that? Write the rate. The rate is 40 rev per minute. Multiply by the conversions. What is your conversion? 1 rev, 2 pi r. If the rev up, what do you need here down? Rev. Up, which is the meters or whatever, yeah? So it's 2 pi r. I'll put it meters because the radius here is meters, yeah? So can I get rid of rev? Now what's the unit? Meter per minute. But I want to change it to second. So another factor. Minute, second. 1 minute, 60. Minute, cancelled with minute. So is this velocity or speed now or not? Okay, what is it now? Do it for me. 40 by 2 pi by r is 2 over 60 meter per second. So final. Decimal. 8.4 meter per second. So you found V, yes? Now can you find AC? V square over R, which is 8.4 square over 2. And you find AC. How much is AC? 8.4 square over 2. 35.3 meter per second square. You got the idea? To convert? Now I want you to think in reverse. Reverse means, suppose I change the question. I give you the acceleration and the radius. Centripetal acceleration is 35. And the radius is? What's the question? At what rate, at how many rev per minute does it do, this object? What you have to do? You start here. R is known, A is known. What you calculate? V. But V will be in meter per. You do this in reverse. Change the conversion. So you change the meters to rev, not rev to meters. Same. Okay? This is the end of it. Now we start on the problem solving of the review. Now I have it's on Blackboard, and you have the sheets, and she can show it there on the monitor. So I'll read the questions for you because I don't want to open the projector. I'll choose some questions. It's always good that you have a printout of each chapter's review problems. Right. On the review problems, if you've noticed that I divided the questions according to the topics. We have 3 topics. The first topic is motion in space. When you have acceleration in X, acceleration in Y, not projectile. So I find the question 1 to question 8 on the review. It's all about this one. After 8, you have projectile motion, motion under gravity. And the third part is about circular motion, yes? So I'll choose questions from each part. Let me choose a question from the first part. Question number 6 from the review. Question number 6. Review chapter 4. I read it. A particle starts from origin at time 0 with a velocity equal, this is the velocity vector, equal to 16I minus 12J meter per second, and moves in XY plane, so in X and Y only, with a constant acceleration. The acceleration is constant, and the acceleration is given. A is 3I minus 6J. The question is this: what is the speed? What is the speed at t equal 2 seconds? This is the question. What is the speed at 2 seconds? This is a question number 6 in the review problems. Right. How do we solve a questions for an object moving in space? We create a table, yes? And in each column we have 5. So I'll put the 5 here for you. Column X, column Y, and R. In X, we have V naught X, we have Vx, Ax, delta X, and time. Same here, V naught Y, Vy, Ay, delta Y, and time. And here is the combinations, X and Y. So here I have V naught vector. Here I have V final vector. And here we have acceleration vector, and here we have displacement vector, and this is time. It's the same old table which we talked about. What we do next? We read the question and we fill. Now here you might get this wrong. It says initially the velocity is what? And you are used to put naught, yes? Add it. But remember, it was talking about initial at time 0. So this is initial. Where does this one go in the column? In column R. So it goes there. 16 I minus 12 J. So if I go back now, how much is V naught X? 16 and minus 12.
Why we say that's initial?
Because it says at time 0, when you read the question, the velocity is this. So this is initial velocity. Now what's the acceleration? 3I minus, so this goes in the third column. 3I minus 6J. which means this is a 3. I'm very sorry, this is velocity. Here. 3. So it's a 3 and minus 6. Now, what do I want? Listen, this is very important. Each time I ask you to find speed, not averages, speed, change the question, find what? Velocity. When we say what is the speed, we mean what is the? So find the velocity and then find its magnitude. It becomes a speed. So what's the question? Find the? Where? Okay, look on the table. This is very important, on the table. Where is this question? In which column? First, second, third. And in which row? What is the velocity? Third. Which row? Second. I want this. Remember, to find final velocity, what do you need? Vx and? So this means find this. Vxi. This is your unknown. Of course, when you find this, what do you do to it? Magnitude, it becomes a speed. Are you with me? Don't forget that. Speed means find velocity. Find the velocity and then find its magnitude. Right. Now, at what time?
2.
So do I know the time?
Yes.
2, 2, 2. Now, tell me, how do you solve? Where do you start? Which column?
The 1, 3.
Okay. 1, 2, 3. What about this one?
1, 2, 3.
So both are operatable, yeah? So will you work on X or Y?
X.
Both, yes? Why you don't work on R? Not possible?
No, it's possible.
Possible or not? 1, 2, 3. But remember, I said avoid working on R when you want to use the equation of dot. But if you can use the other two, don't bother doing this when you can do it here. So if I want V final, V initial, known, acceleration, time, give me the equation of motion for 3 dimensions or 2 dimensions. What is it? Final velocity vector, initial velocity vector plus acceleration vector multiplied by time. Is V not known vector? 16I minus 12J plus acceleration vector 3I time, simplify it, 16I minus 12J plus 6I minus 12J. 16 and 6, 20, 32, yeah? 16 and 6, 22. Minus 24J. What we have found? What's this question? This, no, velocity at 2. What's the speed? Okay, so V is the speed. Equal 22 square plus 24 square. And you find the answer. You got the idea? Now, what you said wasn't wrong. You can work on X to find what?
Find Vx.
And you work on Y. And then you have the same and you do it. Okay, what is the other question you can answer here? What's the question? How far means the magnitude or the vector? Magnitude. But if I say, what is the displacement at 2? It means, how you find delta R? You need delta xi. Now, where do you work? In which column to find this one? This one as well? Or delta x, delta y, you combine them. But let's work on the third one because you're not used to work on the third one. Which equation do you use? Delta R equal V naught vector t plus half acceleration t square, yeah? Do you know V naught vector? Yes. Substitute. A, you find that delta R. When you do that, you'll have I and J. Square them, it gives you how far. So how far means delta R magnitude. This one square and this one squared. This is an extra question. The next question is about projectile motion. So I want to do this one in the last 10 minutes, hopefully. Projectile motion. This is a question number 10. I'm taking a sample of projectile. Question number 10. Review. The question says, suppose you have a gun that fires a shell at an initial velocity of 750 meters per second. So you have a gun, you fire it at what speed, V naught? 750 meters per second. What else? And you aim it, the direction, at 30 degrees above horizontal. 30 above the horizontal. Okay, now so far, can you say it's symmetric or non-symmetric? No, because above could be symmetric or not. From the question you can tell. Now this is the question. How far away will the shell hit the ground? Assuming it hits at the same level. Assuming it hits at the same level, symmetric. So this question is symmetric. All right, now, part B. How long is the shell in air? Which means how long does it take to reach the ground, back to the ground? Time. Third, how high does it rise? Means H max. Yeah? So this is the question. Now we solve it. Starting with the first question. It says how far horizontally? Now let me draw a symmetric for you. Right. I'll repeat the question because I'll just draw it first. Let's say I have symmetric. What's the firing angle?
30.
This is theta naught. And the speed? Of course, if it's symmetric, it goes up and back to the same level, it says, yeah? Start, end. Now, it's symmetric. When it comes to number, at least put 3. Start, number 1. When it's at maximum, number 2. When it hits the ground. Of course, you could add more, 3, 4, between. These are the 3 main ones. What's the question? How far away? How far means distance, yeah? But how far, it could be how far horizontally, vertically, or how far from origin. And this question says, how far away will the shell hit the ground? Here, if you say delta R or delta X is the same. Because this is origin, yes? How far from origin is this, delta R? And this is the same as delta X. So it means find delta X. Find this delta X. What do you call this delta X? Range. This is delta X or range, yeah? This is the first question. Find R. Okay, how do you calculate or how do you solve any questions in projectile? You create a table, but not exactly similar to what we did. In this table, you just put the horizontal function equation and the vertical, what I showed you in the beginning of the class. So X, I have delta X, V naught, cosine theta naught multiplied by T, and I have Vx, V naught, cosine theta naught, and here we have Vy, V naught, sine theta naught minus GT, and we have Vy square, V naught, sine square theta naught minus 2G delta Y, and we have delta Y equal V naught, sine theta naught, T minus half GT square. Is that complete?
No, there's 2.
There's 2 more because it's symmetric. Yep. R, V naught square over G multiplied by sine twice of the angle. and H max V naught square sine square theta naught over 2G. What's the question? Find what? Okay. You can answer this question in 3 different ways. Easy way. This is the equations of R, yes? What do you need to calculate R? V naught and theta naught. Given or not? Easy. But don't learn the easy way. Learn the hard way. So, you know. When you want R, R is horizontal or vertical? So where do you work? On the horizontal, X. How many equations you have in X? No, 1 and a statement. This one. So I can think of delta X as R. If I put delta X R, which time is this? Yeah, but which time? From 1 to 3. Is the time given? Okay. So to answer, if you take this as R, V naught, cosine theta naught, you have to say this T is from 1 to 3. Is V naught known? Yes. Theta naught? So if I find this T, I find R. So remember, T is the key. You can take it from X to Y, from Y to. So go to Y now. This got T, this one got T. Which T you want? From 1 to? So you have to apply these equations from 1 to 3. If I want to use this one, V naught, known. Theta naught, Vy here. Which Vy is this? At which point? It means this. Here. Vy here. Remember here you have Vy, you have Vx and V3. It means Vy at 2. Is it given? Is it given? No. But can you calculate it? Because it's symmetric, Vy here equal to V naught Y, but opposite, which means whatever you calculate here, this is V naught Y, yes? V naught sine theta naught. Let's say this is 4. What do you put here? Minus 4. It means you're finding time from 1 to 3. Are you with me? Whenever you put Vy opposite of V naught Y, it means there are 2 points at the same level. One up, one down. So when you put Vy equal to this and opposite, it means you're talking about the time start to finish in this case, yes? Start to. So if I find the time, I put it here. I find the range. This is the second method. Third method. This equation has time or not? Which time I want? 1, 2, 3. So what I have to know? V naught known, theta known. What else I have to know? Which delta Y? From 1 to 3. What is delta Y between 1 and 3? Well done. So when you put delta Y equals 0, you're talking about 1 to 3. So if I put delta Y 0, it means I'm calculating which time? 1, 2. And then you find it, you find out. I gave you 3 ways for one question. Second question, B part. What is it? How long is the shell in air? How long is the shell in air? Which means find which time? How long the shell in air? Total time from 1 to 3. We want T from 1 to 3. Did we answer this question or not? I already answered it for you. If you want T from 1 to 3, what you have to know, if you're talking horizontally, this is 1 to 3, unknown. Imagine it's unknown. What you need? V naught and the range. You found it from this equation. That's if you're working horizontally. But now vertically. If you want T 1 to 3, what you have to know? These two, yes? These are known. This one, opposite of this. If you use this one, put delta Y, 0. Done. Third question. How high does it rise? How high does it rise? Means h, which is delta y between 1 and 2. Now, if you want delta y between 1 and 2, there is the easy way, h max. V not known, theta known. That's direct. Hard way. There is delta y here, yes? To find delta y from 1 to 2, what do you need here? V naught, this is known. Theta naught? What else do I need? At what point? At 2. Hold on. Vy at maximum is 0. So whenever you put Vy equals 0, it means you're doing calculations between 1 and 2. Let's take the third one. Third one, because I want delta y, yes? From 1 to, so this is unknown. V not known, theta known. Which time? Given? You did it before. Do it again. What's the time from 1 to 2? Half of what you did before. You found it, half of it. You see, this question can be solved in different ways, yeah? So this is the question number 10. Please, I'll take 3-4 minutes. One question horizontal and I stop, yeah? If you don't mind. I know. So you are ready then. But the next time I see you, I'll do more practicing. So question, it won't take long. Question 15. Question 15. I read it quickly and I'll give you a sketch. A ball is thrown horizontally from a top of a building which is 100 meters high. The building, 1 meter high. The ball strikes the ground at a point 65 meters away from the building, horizontally. What is the speed? Change it to, what is the velocity? Magnitude. What is the speed of the ball just before it strikes the ground? Just before it strikes the ground. I'll do a sketch here for you. You'll find how easy it is to be solved. So it's question 15. This is what is given. This is the diagram. A building, the height h, 100 meters, and here you're firing horizontally. So V naught is horizontal. But is it given V naught in the question? No. It hits a target, a distance 65. The question, with what speed it hits the ground? So if I say this is point 1 and this is point 2, what do I need here? V2. And to find V2, what do you need? Vx and Vy at 2. If you know Vx and Vy at 2, how you find V2, the speed? V2 as a speed is equal to Vx square plus Vy square under the root at 2. Yes? Okay, now let's go to the table. Standard table. When you fire horizontally, what does that mean? Don't forget that. Theta naught is? 0. So now let's modify the equations here. If theta naught is 0, cosine theta naught? 1. So this equation becomes? V naught t. And this one? Vx equal? Of course, this is Ax always 0. Here what happens? This will disappear. It becomes minus gt. This one disappears. It becomes minus 2g. And this one will disappear because sine 0 is 0. And you'll have minus. And what else disappears? Those two equations. Right. Start from the question. You need Vx and Vy. Look at the table. Where is Vx? Which column? To find Vx, what you have to know? V0. Where is V0? Still in x, yes? So you have to find this. What do you need? Delta x and? Okay. Do I have a delta x? Between 1 and 2. How much is it? What else I need? The time from 1 to 2. Given? What you do when you don't have the time? You go to y. Between the same 2 points. Now, between 1 and 2, vertically, what do you know? You need delta y. But you need time, remember. So, is this equation useful? No, because this one? No, this one. Delta y. How much is the delta y? Minus 100. Minus, because you start at this level, you finish at a level below. Delta y is negative. Minus 100. So put minus 100 here. Minus half. 9.8 t squared from 1 to. When you find the time, you'll find? So now you know Vx or not? We finished the question? No. We need? Vy is here. Between 1 and 2. It means Vy at 2. At 2. What do you need? From 1 to 2. Known? Good. Or here. What do you need? Between 1 and 2. Known? Minus 100. Both ways you do it. And plug them in here. So thank you for coming. And I'll see you next time. But please let me take the attendance before you go. Quickly.